Hello and welcome to this talk on cut vertices in random planar maps. I'm Benedikt Stufler and this is joint work with Drmota and Marc. Randomly generated planar maps, such as in this illustration, have been intensely studied throughout the past decades. Yet, we ask ourselves a very basic question that turned out to be way more complicated than anticipated. How many cut vertices does a random planar map with n edges typically have? Maybe let's start by recalling some background. A planar map may be defined as an embedding of a connected multigraph into the two-dimensional sphere. Here, vertices are represented by points on the sphere and edges are represented by non-self-intersecting arcs. We require that any two different arcs may intersect only at their endpoints. Usually, we fuse such embeddings up to continuous deformations. That is, two embeddings are equivalent if one may be obtained from the other by applying an orientation-preserving homomorphism of the sphere. In order to eliminate symmetries, typically we distinguish an edge and give it an orientation, like this. When drawing a planar map, we may either draw it on the sphere or in the plane by applying a stereographic projection. Since we are only interested in embeddings viewed up to continuous deformations, we may take some liberties in choosing the coordinates. For example, we may tell Mathematica to choose the coordinates according to some spring electrical embedding instead of placing them on the sphere. This was done in the illustration we saw on the first slide. Since we view embeddings up to continuous deformations, there are only finitely many planar maps with a given number of edges. Tutt in the 60s actually calculated the precise number. In the bottom left corner, I've listed all planar maps with one edge, and in the bottom right corner, all 9 planar maps with 2 edges. It is usually notationally convenient to make an exception for the trivial map that has one vertex and no edges at all. We interpret this map as a rooted planar map, although it has no edges to be rooted at. A vertex V in a planar map is called a cut vertex if we may partition the edge set of the map into two non-empty classes E1 and E2, such that V is the only vertex incident to edges of both E1 and E2. In the pictures below, I've colored all the cut vertices in red. Likewise, in this picture of a randomly generated planar map with 500 edges, all cut vertices have been colored in red. The coordinates of these vertices have been chosen according to some spring electrical embedding of Mathematica. You may see that it's not crossing free, that's unfortunate, but we can still get a little bit of a feeling for the number and distribution of the cut vertices in the planar map. Our main result states that the number xn of cut vertices in a uniformly selected planar map with n edges is linear in n. Specifically, we show that xn divided by n concentrates around the constant 5 minus square root of 17 divided by 4. Now, when doing long and complicated calculations of constants, it's easy to make a mistake that goes unnoticed. However, we are very confident that we have obtained the correct constant because we've actually come up with two very different approaches in proving this result that yield the same constant. The first is more of a probabilistic approach that is based on recent results on the local structure of planar maps. Second uses a combinatorial approach and describes in detail the enumerating generating functions. This approach may also be used to, at least in principle, calculate the higher moments of xn, although the details become quite intricate. We've also made simulations of around 200,000 samples, each having precisely 500,000 edges. And the average number of cut vertices obtained is already very close to the constants obtained in the proofs. The first 6 digits after the dot were correct. Having obtained concentration, it is natural to ask about the precise asymptotic behavior of the fluctuations. We conjecture that a normal central limit theorem holds. This conjecture is backed up by simulations. If you look at the histogram for the number of cut vertices, you see this bell-like shape that is characteristic for the density of the normal distribution. I will briefly sketch the main proof ideas of the probabilistic proof. We let Mn denote the random planar map with n edges, and we let Bn denote a uniformly selected vertex of this map. It is known that this pair admits a distribution limit m infinity in the local topology. That is, we look at the collection of all locally finite vertex-rooted planar maps, and we equip this collection with a metric that essentially says that two such vertex-rooted maps are close to each other if large vicinities of their roots are isomorphic or equivalent. Now, our pair M and Bn may be interpreted as a random element of this space, and M infinity is then a distribution limit of random elements of this space. When we consider the following functional on this collection, the indicator variable for the root to be a cut vertex. This indicator variable is not continuous on the entire space. For example, if we look at a sequence of cycles with an increasing circumference, if we look at the vicinities of random points, that is k neighborhoods for a constant k, that is all or the submap obtained by all vertices with graph distance at most k from that marked root, then we see a path as the circumference of the cycles becomes large. That is, although none of these cycles has a cut vertex, the limit is a doubly infinite path and has the property that all of its vertices are cut vertices. So this indicator variable is not continuous on the entire collection, but it is continuous on a subset. So what is this subset? Subset of all maps such that either the root is not a cut vertex, or the root is a cut vertex and deleting it creates a finite component. Essentially, suppose that we have some sequence of vertex rooted maps that converge to a limit in omega. Now, if the root of omega is not a cut vertex, then either it's a leaf or it's contained in some finite cycle. But both being a leaf or being contained in some fixed cycle of a given length are local properties. So this is already something we can then see in elements of this sequence approaching the limit. Or if the root is a cut vertex and deleting it creates a finite component, then this finite component must already be present in almost all elements of the sequence. Now, suppose we can show that M infinity lies almost surely in omega. Then by the continuous mapping theorem follows that xn divided by the number of vertices of mn has a first moment that converges as n becomes larger to a constant p, given by the probability that the root of M infinity is a cut vertex. Now the number of vertices of Mn concentrates around n half. This is something you can show by some basic symmetry arguments. So this is actually asymptotic to first moment of xn divided by n half. Now we have an expression for the first moment. So why can we get a stronger law of large numbers? Now, in fact, there's a stronger form of local convergence that is known. This so-called quenched local convergence. This is the conditional law of the rooted version given the map. That's a random probability measure. It converges in probability to the law of M infinity. That is, here on the left side, we look at a random measure. So we take Mn, this is where the randomness comes from, and then if we have Mn, we have a finite number of vertices, and so we have a finite number of rooted versions, and we take the uniform measure on this rooted versions. So that's a random probability measure, and it converges in probability to the law of M infinity. That's a priori at least stronger form of convergence. And using this stronger form of convergence, and again the continuous mapping theorem, we actually may deduce a law of large numbers. Now, in order to prove our main theorem, there are two things left to be done. First, verifying our lemma that M infinity lies almost surely in omega. And second, calculating this probability that the root of M infinity is a cut vertex. I'll just very briefly sketch the proof of the lemma. It uses the so-called Boltzmann distribution of planar maps. There's a distribution on the collection of all finite planar maps. So let M be a random variable with values in the collection of all finite rooted planar maps that follow the Boltzmann distribution. So here E of M denotes the number of edges of a finite planar map N. Okay, the main idea of the lemma is that so there is a random map M infinity star with the property that its root is not a cut vertex. So there is such a map with the property that M infinity is distributed like the result of attaching an independent copy of MB at each corner incident to the root of M infinity star. So for example, if this depicts the local structure of M infinity star, then we attach independent copies of MB at each corner incident to the root. So the number of copies we attach is equal to the degree of the root of M infinity star. Now, why does such a map M infinity star exist? We may view the map Mn as the result of attaching planar maps to each corner of its largest non-separable submap as its two-connected core. And the random vertex Bn is either going to be part of the core or it belongs to a unique component attached to it. The core commits a random infinite non-separable planar map as its limit. All components attached to the core that are visible in the vicinity of Bn asymptotically behave like independent copies of MB, except the component containing Bn. Asymptotic distribution is not MB but a size-biased version of MB, and we know precisely how to describe this size-biased version. So having this structural information at hand, we know the shape of M infinity, and we can construct M infinity star as the uniform, infinite, non-separable planar map with size-based map attached to it, lots of copies of MB attached to it, except for the copies that we would attach where the root location is. This proves the lemma. Now, if we construct M infinity this way, by attaching independent copies of MB to the root of M infinity star, then we know that the root of M infinity is a cut vertex if and only if at least one of these copies is non-trivial. That is, if at least one of these copies contains an edge. And if we recall the distribution of MB, the probability for MB to have no edges at all is given by 3/4. If we, let's say, Q of z, not the probability generating function of the root degree of M infinity star, let Qk denotes its coefficients, then P is equal to sum over k, so probability that the root degree in M infinity star is equal to k, and then the probability that at least one of these k copies of MB is non-trivial, so that's 1 minus 3/4 the power k, and this simplifies to 1 minus Q of 3/4. Furthermore, the root degree of M infinity is given by the root degree of M infinity star plus the sum of the root degrees of the independent copies of MB. Hence, the generating function for the root degree of M infinity is given by Q of that times the generating function for the root degree of MB. Now, the Boltzmann map is intimately connected to equations of generating functions for counting planar maps. This allows us to apply Tutt's quadratic method to obtain the following expression for the argument of Q. The root degree of M infinity is the limiting distribution for the degree of a random vertex in Mn. Now, this limiting distribution is not totally explicit in the literature, but by combining results of Gauss enrichment and Liskowitz, we can obtain the following expression for its probability generating function. Now, if we take a pre-image of 3/4 this function and plug it into this equation, we obtain an expression for Q of 3/4. And with Q of 3/4, we obtain P. With P equal to 5 minus square root of 17/2, it follows that our limiting constant P/2 is given by 5 minus square root of 17/4, hence completing the proof of our main theorem. I thank you for your attention and hope you've enjoyed this talk.